Okay, sir. So, sir, thank you so much. And tomorrow we will meet again for the second session of your talk, sir. Thank you so much,
Perfect.
sir. Thank you so
Okay,
much.
thank you. Thank you very much.
Yes, sir.
And good night to all of you.
Good, sir. Uh, okay, participants. For the today's second session, we are pleased to have Dr. Gurmohan Singh, sir, the Joint Director of CDAC Mohali. Gurmohan, sir, please unmute yourself.
Hello,
Good evening, sir.
good evening. Am I audible?
Yes, sir. Yes, sir. You're audible. So, once again, good evening, sir. A very warm welcome to AICT sponsored Atal FDP. Thank you for joining us. It is my great privilege and honor to introduce today's distinguished speaker, Dr. Gurmohan Singh, Joint Director, CDAC Mohali, an eminent expert in the field of quantum computing. Uh, Dr. Gurmohan Singh is a joint director and scientist E at the CDAC Mohali, specializing in quantum computing and cyber security. With over 19 years of experience in research and development, he has made significant contributions in the field of quantum algorithms, machine learning, and VLSI design. He holds a PhD from NIT Jalandhar with his thesis focused on automata based circuits. Dr. Singh has held various key positions at CDAC, making him a key figure in advancing research and innovation at CDAC. Dr. Singh's research interests include quantum computing, quantum machine learning model, quantum circuit optimization, and quantum application and use cases development. He has supervised multiple PhD and more than 50 master's theses, published more than 60 research papers in reputed journals and conferences, and played an active role in organizing quantum computing workshops and training programs both nationally and internationally. For his exceptional contributions, he received the prestigious award in 2020 for CDAC for implementing a high value project, and his work continues to influence the future of quantum computing and cybersecurity in India. Respected sir, participants are eagerly looking forward to your talk. May I request you please begin your talk, sir?
Okay, thank you, Mukesh, for very wonderful uh, my reading for my reading bio profile. Okay, so should I share my slides first?
Yes, sir.
Okay, please, my slides are visible.
No, yes, sir. It's visible.
Okay. I'm not able to actually see my slide. Okay. Okay, now it is visible.
Yes, it is visible.
Okay. So good evening, everyone. So today my talk is on quantum computing, basically from gates to algorithms. How we are basically working on quantum gates, then quantum circuits, and then to what kind of algorithms in quantum that has been already developed and being used. Okay, so you can, I think, from earlier sessions, you might have known what is the potential of quantum computing. Okay, so we can, if today's supercomputer took 10,000 years to solve a problem, how would you feel if a new machine, quantum machine basically, it solved this problem in 200 seconds? That Google has already claimed in 2019 when they claimed that they have achieved quantum supremacy. Okay, so basically what they have
Uh,
done, they have
sir,
taken, hello.
sir, sir, kindly make the slides full screen.
Oh, I think it is full screen.
Uh, no, sir. Actually, we are not able to. It is not full screen, sir.
Now it is full screen.
Uh, no, sir.
Okay, let me stop the sharing. Then again, I will.
Okay, sir.
Now
Yes,
it
sir.
is
No, yes, sir. Yes, no, it is full screen.
okay. So, Google has what Google has done in 2019. They have basically they developed their own 53 qubit quantum computer, and on that they run particular problem, computational problem, and that problem it solved within 200 seconds. And it was estimated that if that problem they run on world's fastest supercomputer at that time, it might have taken more than 10,000 years. So this particular kind of example, it shows that what kind of potential this technology is having. So in this presentation, I would be covering a brief introduction to quantum computing. Basically, what are the fundamentals of quantum computing? Then what kind of quantum gates that we use in quantum computing? Then what kind of algorithms are there in quantum computing? So we all know that 19th century was known as machine age because a lot of machines were developed in that particular period. And 20th century will be remembered in history as the information age, as we already know. Then it is predicted that 21st century will be remembered in history as quantum age. Okay, so we all know that in industrial, in sorry, 19th century, lot of machines, mechanical machines were developed. That is why that particular period is called industrial revolution. Okay, like steam engines were discovered in that particular era. Then transistor was developed in 20th century, and it has brought a IT revolution. We all know. Okay, then now it is predicted that quantum computing it may trigger a computational revolution in 21st century, and it will be remembered as quantum age. So, coming to what kind of supercomputing facilities India is having, so India's we can say uh, strongest supercomputing machine that is available with CDAC is Param Airavat, and its capacity is 3 AI exaflops. Means it can perform 3 exaflop operations. Means floating point operations 3 into 10 raised per 18 operations per second. So this kind of machine is already India is having, and it is ranking among world's top 500 computers, and its rank is 76th in the world. So it is predicted that if we are having a fault tolerant, or we can say logical quantum computer with 100 logical qubits, then it can, we can say, it can over or surpass the computational capabilities of all the supercomputers in the world. So what is actually Moore's law? Quantum computing basically its origin starts from Moore's law only, because Moore's law has given us transistor. Okay, then how number of transistors on an integrated circuits they will keep on doubling. He has predicted this in 1965. He has just given a, we can say, observation based on the production experience. Okay, what kind of production was there at that time? He has given this particular statement, and this statement holds true till last decade. Okay, so number of transistor on an integrated circuit, it kept on doubling after every 2 years. Now its rate has slightly reduced, and now it is doubling in 2.5 to 3 years. Okay. So in 1959, Richard Feynman, he has given a theory that there is plenty of room at the bottom. What does that mean? Basically, it means that he said that we now at present in transistor we were computing using currents and voltages. Okay, so we represent zeros and ones in the form of currents or voltages. Okay, so in this Richard Feynman has said that in atom there are a lot of things like protons are there, okay, neutrons are there, electrons are there. We can use these kind of subatomic particles for computation or for representing different kind of states like zeros and ones. Okay, so he has given this statement, there is plenty of room at the bottom. Okay, so in quantum computing we use what kind of particles we use? Subatomic particles like electrons, okay, protons, okay, these kind of particles we use in quantum computing for representing different kind of states. So when we see for what kind of applications, there is obviously the question what for what kind of applications quantum computing is best. Okay, quantum computing is not going to replace the existing computers, because quantum computers of their own they cannot do, and they cannot do all the things. Okay, they need classical computers for giving them the inputs. Okay, then classical output devices to read the output from them. Okay, so quantum, what for what kind of problems quantum computer is best? Okay, so we will see examples. What is an exponential growth? We might have seen that in computational problem we see that if something grows at a consistent rate and something grows very faster. Okay, so when growth becomes very rapid in relation to, we can say, growing the input quantity, then it is exponential. We call it exponential. Okay, so this kind of graph is there for exponential growth. Okay, so this is an example of what is an exponential growth. Okay, so there is an old story in which a king, okay, he promised a particular person, okay, that he will award him, okay, a prize because he has solved some problem of the king. Okay, then he asked the ruler, okay, or the king to reward him by placing 1 grain of rice on first square of chessboard, 2 grains on the second, and 4 on the third, and so on. Okay, so every scale was to have the double the number of grains as the previous scale. So king did not estimated this thing that this could be very large also. Okay, so he granted the request, but soon realized that rice required to fill the chessboard was more than the existed in the entire kingdom and would cost him all of his assets. Okay, so guess how many rice grains you get on the last square of the chessboard? It is approximately 18 quintillion, means 18 into 10 raised to power 18. Okay, so this much of the rice he might be having, rice grains he might be having to give to that particular person. Okay, so these kind of problems where the exponential growth kind of problem is there, or problems like optimization, many of the optimization problems are there. Okay, like in COVID, we were all were expecting that why COVID vaccines are not coming much earlier to us. Okay, but if you see a COVID from the market, what kind of COVID vaccines are available? Okay, so all these vaccines they are containing more than 50 to 130 molecules. Okay, 50 to 130 molecules. 50 to 130 molecules. If you run all the combinations of those molecules, it starts from 2 raised to power 50 up to 2 raised to power 130. Okay, so running all these combinations on existing classical computers, it might have taken years. Okay, so that's why a successful drug discovery or drug design, it takes more than 5 to 10 years. Okay, because each we have to test each and every possible combinations. So in COVID case, what the drug manufacturers have done, they skipped few combinations. Okay, so nobody knows what kind of effect those kind of the combinations of molecules those have been skipped in those drugs, what kind of effect those kind of molecules or combination is having on our health. Okay, so that is why now it is coming to light that they are having so many, we can say, side effects. So what is actually quantum computing? Okay, it is totally new type of computing paradigm. Okay, it basically uses principle of quantum mechanics. Okay, to solve extremely complex problems very quickly. It is having very high potential to solve very complex kind of problems that are beyond the limit of today's computers. Okay, so basically what the problems which are mathematical in nature, okay, the problems of which can be modeled as in mathematical terms, those kind of problems it can solve very easily as compared to classical computers. So this is basic brief, very brief history of quantum computing. In 1982, Feynman proposed the idea of creating machines based upon laws of quantum mechanics. Okay. Then in 1985, David Deutsch developed the quantum Turing machine, showing that quantum circuits are universal. Universal means they can also implement many type of functions. Like classical, in classical, we are having NAND and NOR gates. Okay, those we call universal gates because using those gates we can implement any other type of gates. Then in 1994, Peter Shor came up with quantum algorithm to factor very large numbers in polynomial time. So basically, this is a basically algorithm which is having potential to break today's encryption, provided we are having a quantum computer with sufficient number of qubits. Okay, so uh, in 1997, Love Grover, an Indian, he developed a quantum search algorithm and he predicted that it can quadratically reduce the complexity of search in in an unstructured database. So what kind of quantum mechanics principles are there? Those we can say quantum computers use or those form the basics of quantum computing. So basically there are two main principles. One is superposition and other is entanglement. Okay, so these two principles they give we can say a lot of power to quantum computer to perform the various kind of difficult operations uh, in a in a much faster speed, okay, than classical computers to solve difficult kind of problems like factoring very large prime numbers, okay, simulating molecules and optimizing large systems. So what is basically a quantum bit? In classical, we are having a bit, Boolean bit. Okay, it can have only two states, 0 or 1. In quantum, equivalent of classical bit is quantum bit, or in short, it is also called qubit. Qubit is the basic unit of information in quantum computing. Okay, in quantum computing, the information is encoded in qubits, and a qubit can be in state 0, 1, or any linear combination of this 0 and 1 simultaneously. Whereas in classical, we were having that our bit could be either 0 at a time or it could be 1. It cannot be in any of those 0 and 1 simultaneously. In quantum, our bit qubit can be in 0 and 1 simultaneously or any combination of 0 and 1 also. So this phenomena is called superposition basically. So what are basically key properties of a qubit? So first is the superposition. A superposition says that a qubit can be in multiple states simultaneously. For example, we represent qubit as a size equal to alpha ket 0 plus beta ket 1. Here alpha and beta are the we can say complex probability amplitudes. Okay, alpha is the amplitude of your state being into probability. What is the probability that it would be zero, cat zero, and beta is what is the probability it would be cat one. Okay, so second is entanglement. What is entanglement? Basically, when we put two qubits together, they interact with each other. These are basically subatomic kind of particles. They interact with each other. They acquire properties of each other, few properties of each other. Okay, and they keep on acquiring those properties of each other, even if they have been separated from each other. Okay, so these kind of things, they are very, we can say, useful in quantum communication. Okay, secure communication also. Okay, so second thing I want to highlight here, that we cannot copy a quantum state. Okay, no cloning theorem is there which says that we cannot copy a quantum state. Okay, so what does it mean? No one can hack quantum information. If there is communication between Alice and Bob already happening, okay, someone tries to hack the information between them, okay, then it would collapse and he would get nothing. Okay, so quantum communication is very secure kind of communication. Then quantum measurement is there. Okay, if I want to take we can say output from my quantum system. Okay, then qubit collapses to either cat 0 or 1. Okay, with the probabilities, those can be calculated using magnitude of, what is the magnitude of alpha and beta. Okay, so uh, for quantum taking the measurement, I always need a classical kind of registers. Okay, so when quantum qubit collapses, its state is transferred to classical, we can say, register kind of thing. Okay, then quantum gates are there. Qubits are manipulated using quantum gates. Like in classical, we are having different type of gates, like like NOT gate, AND gate, OR gate, NAND gate, XOR gate. Okay. Similarly, in quantum also, for performing different types of operations on qubits, okay, we are having different types of gates like Hadamard gate, poly gate, poly matrices also. We sometimes we say different types of poly gates are there, X, Y, Z. We will see all of these in detail. Then C naught gate is there for creating the entanglement. Okay. So this is basic qubit representation using Dirac's notation. Okay. So it is, we can say, way of representing quantum states. Okay. So it was named after scientist Paul Dirac, who developed the notation in 1930. So it is widely used, or we can say mainly used in quantum computing to describe quantum states, quantum operations, and quantum measurements. Okay, so here we have already seen that what is alpha, what is beta, and what is the magnitude of cat 0 and cat 1 state. So what kind of physical implementation of qubits are there? Okay, so like in transistors, we were having bipolar transistors, MOSFETs were there. Okay, bipolar transistors, basically they were using three kind of junctions: base, emitter, and collector. Base was controlling the current between emitter and collector. Similarly, we were having MOSFET. In MOSFET, gate voltage control the current between source and drain. Similarly, in quantum, what how all these kind of operations are performed? There are different kind of semi, we can say, qubits. Qubits are nothing, they are similar devices like transistors. Okay, in quantum these are called qubits only. There is no name like transistor. Qubits are called qubits, they are physical devices basically. So there are different kind of, lot of technologies are there in which we can fabricate qubits. Okay, like superconducting qubits are there. Okay, so superconducting qubits, they are being used by IBM, Google, or Getty. Okay, then trapped ions are there, they are being used by INQ company, Honeywell. Then photonics qubit, lot of companies are there in photonics. This one is Xandu is a Canadian company. They are prominently working on this particular kind of photonic technology. There are a lot of companies in India also as well as in China, okay, who are working on this particular technology. Then topological qubits are there. This is very recent, and Microsoft is developing these kind of qubits. So, what is actually quantum superposition? How it provides quantum computer with massive parallelism. Okay, so in classical, we see that if we are having n number of input states, okay, so then what is the possible number of combination of input states? It is 2 raised per n states. Okay, so if classical logic, we give those states 2 raised per n state one by one to classical logic, okay, then it can give output one of the 2 raised per n states at a time only. Okay, it means it will give us one input as output or some kind of manipulation of input as output at any instant of time. Okay, so parallelly, if we see, we are having quantum logic. Okay, so if we are giving 2 raised per n states possible input combinations to the quantum logic, then it will give us all the we can say superposition of 2 raised to power n states simultaneously. So it provides quantum computers with massive parallelism. Okay, it evaluates all the input combinations simultaneously. So these are, for example, we are having two qubits, okay, in quantum computing. So there are four basic states, okay, cat 00, cat 1, 10, 101, 11. Okay, so we run these four combinations on our quantum computers. Okay, so in quantum computers, existing quantum computers are noisy devices. They contain lot of noise. Okay, so we run that particular combination multiple times so that we can say with 100% surety that this is the final output and this is the most stable output. So we run 100 times that particular computation. It will give us all the four combinations. What is the possibility? For example, 01, it roughly runs 50 times. 10, it roughly runs 17 times. 11, it roughly runs 33 times. Then what is the highest probability? Which state out of these, okay, 01, 10 or 11 is having highest probability? That is assumed that this would be the final state of my quantum computer or quantum computing system. For example, I am having independent qubits. Okay, superposition says that qubit can have both the states simultaneously, zero state as well as one state. Okay, so there might be probability that my qubit will be in state 060 with 60% probability, means my alpha is 0.6. Okay, and beta is 0.4. Okay, as we have already said, this alpha is representing magnitude of my state being into cat 0 state. Okay, and beta is magnitude of my probability of we can say my state quantum state being into 1 cat 1 state. Okay, so similarly, my qubit can having simultaneously, it could be having probability that 60% probability of being into 0 state and 40% probability of being into 1 state. Similarly, it could be having other probability like 15% probability into 0 and 1% 85% probability into 1 state. So now these were the independent qubits. Okay, now in entanglement, I put many qubits together. Okay, so when I put many qubits together, their probabilities are also become joint probability as a single state. Okay, because they acquire properties of each other, they influence the state of each other. Okay, so so if I see an entangled, we can say qubit pair. Okay, so what kind of probabilities could be there? Okay, two qubits are there. So when I run my system, it is giving me probability, different probability, 0, 0, 25% probability. It is saying me in quantum, your outputs are always like this. 0, 0 probability is 25%, 0, 1 probability is 1, 0, we can say 10% only, 10 probability is 40%, and 11 probability is 25%. So what would be the output in this case? because it is giving for all the four probability, four input combinations, it is giving me different probabilities for all the input combinations. So my output would be the state which is having highest probability, means 40%. 10 would be my output in this particular case. So coming to this is quantum computer, we can say view how quantum computer looks like on right side. Okay, so this is basically super conducting qubit kind of quantum computer. So what are different areas in quantum technology? Okay, so there are a lot of different areas like quantum computing is one, then quantum communication, quantum metrology and sensing, quantum materials. So India has in 2023 they have launched National Quantum Mission, which is with a budget of 6,000 crores. Okay, so accordingly, they have recently created four thematic hubs in all these four areas. Okay, and they are basically spearheading the quantum mission in the country by inviting different kind of research proposals. So how does quantum computer looks like? Okay, so China has a 12 photonics kind of quantum computer. They are working on other technologies also. So this is a 76 qubit photon based quantum computer. So in photon based quantum computers, the problem is lot of control circuitry is very complex actually. Okay, so and a lot of big kind of setup is required for the photonics kind of technology. Then INQ is there, ion trap based 32-bit quantum computer is there. Okay, so then this is having peak of 53 qubit superconductor based quantum computers. Okay, from IBM. So at present, all these kind of technologies they are suffering from many limitations. Also, the qubits in these technologies are a lot of noisy. They cannot in like superconducting. They cannot operate at room temperature. They can operate in cryogenic kind of temperature range only. In superconductor qubit based technology, they can operate between 5 millikelvin to 15 millikelvin. Okay, this temperature is below absolute temperature. Okay, so that is the biggest kind of hurdle in these kind of technologies. So now coming to our main topic, what kind of quantum gates are there? Okay, so what are quantum gates? Basically, they are the building blocks of quantum computers. Okay, quantum operations. Okay, they perform operations on qubits similar to logical or similar to classical logic gates. Okay, in classical circuits. Okay, unlike classical gates, all quantum gates are inherently reversible. In classical we don't have any, we can say, reversible gate, although some people claim that not gate is reversible. Okay, but all other gates are not reversible, means we cannot backtrack the input from the output. Okay, in class quantum computer all the gates are reversible in nature. Then quantum logic gates are represented by unitary matrices. So in quantum computing, when we talk about gate is, we can say, performing some sort of uh, matrix expression on the input. Okay, so all these gates are represented by some kind of unitary matrices. So then there are two broad categories of quantum gates. One is the single qubit quantum gate, other one is the multi-qubit quantum gates. Okay, single qubit gates they can perform only on one qubit, and multiple quantum qubit quantum gates they can perform on multi-qubits. Okay, so coming to single qubit gates, we are having broadly four different categories. Poly gates, okay, then Hadamard gate, then there are phase shifter gates, then general U gates are there. Okay. So now coming to one by one, we will first cover single qubit gates. Okay. So in single qubit gate, the most prominent gate is poly X gate. Okay. In classical, we were having NOT gate. In quantum equivalent to NOT gate is poly X gate. Okay. It is basically single qubit gate. Okay. And flip it basically flips the state of qubit. Okay, its mathematical representation of its matrix is like this 0 1 1 0. Okay, so when we apply this particular matrix, or we can say gate, to a qubit, okay, so then it converts, if it is qubit cat 0, then it will convert to 1, and if it is cat 1, it will convert it to cat 0. So its applications are basically into flipping of state of qubit. Then it is a basis of forming other complex quantum gates and operations. It is widely used in quantum error correction algorithms and initializing quantum states also. Then we are having another important poly gate. It is called poly Y gate. What does it do? It basically do both the things. It flip the phase as well as amplitude. Okay, so it only flips the phase of, we can say, state 1, cat 1. Okay, it does not flip the phase of cat 0. Okay, it applies a 180-degree rotation of qubit around the y-axis of Bloch sphere. It basically combines the effect of poly X and poly Z gate. Poly X gate flips the amplitude of the qubit, and poly Z gate basically flips the phase only, and poly Y gate flips both phase and amplitude. Okay, its matrix is like this, and when we apply this to basically cat 0, it will invert its amplitude, but there will be no phase shift in this case. But when we apply this to cat state 1, then it flips the phase as well as amplitude of it. So basically this poly bigate is widely used in quantum states rotation. Then it is essential in specific quantum algorithms. Then it is widely used in error correction and generating different kind of phase sequences. Then polyjet gate, it is widely used for flipping the phase of a quantum state. Okay, so it might be remembered that it only flips the state of one cat 1 state only, while leaving the cat 0 state unchanged. Okay, so its matrix is like this. Here it is wrongly written poly Y matrix. It is basically poly Z matrix. Okay, so it is widely used in flipping quantum state manipulation. Then used in constructing more complex gates like Hadamard gate. Okay, then integral to quantum error correction and phase estimation kind of algorithms. Now coming to very important gate in quantum computing, it is Hadamard gate. It is also single qubit gate, and this particular gate is basically used for creating the superposition. We say that in quantum computing that our qubit can be into state 1, into state 1, into state 0, and it could be simultaneously in 0 and 1. Okay, how it could be simultaneously in 0 and 1? This is basically the state, Hadamard gate, which puts the qubit into superposition of 0 and 1. Okay, so it transforms a qubit from a basis state. In quantum computing, what are the basis states? Basis states are like cat 0 and 1 are the basis states. Okay, so there are other basis states also. If we apply Hadamard gate on qubit 0, it becomes basis state plus cat plus. Okay, then if we apply Hadamard gate on cat 1, then it becomes another basis state cat minus. Okay, so for example, its matrix is like 1 by under root 2, 1 1 1 minus 1. Okay, when we apply Hadamard gate to basically this qubit 0, okay, this 1 0 is basically nothing, it is a cat 0. Okay, so this cat 0 is represented in vector notation, or it is written like this. Okay, 1 0. Okay, 1 basically here 1 is representing probability of cat 0 into being 1. Okay, so it is representing probability of cat 0 state, and it is 1. Okay, so it is representing cat 0. Okay, so when we apply Hadamard gate on cat 0, so what we get? We get 0, cat 0 plus cat 1 under root 2. This is the output of Hadamard gate, and when we apply it on 1, we get cat 0 minus cat 1 by root 2. This is these two are called superposition states basically. Okay, so the major applications of Hadamard gate are in preparing the quantum state into superposition states. Okay, they basically provide us with massive parallelism, then quantum Fourier transform, which is basis of Shor's algorithm. They are widely used in that. Then Grover's algorithm, which initializes a uniform superposition for searching. Then we are having well state creation. Okay, well states are nothing. They are the maximal entangled states. Okay, for example, we are having two qubits. Okay, so how we can entangle them. Okay, so that they become maximally entangled. Okay, so for that we use Hadamard gate in combination or in combined with C naught gate. Okay, for creating the well states. So C naught gate is basically used for creating the quantum entanglement. So then there are a lot of other gates, like phase shifter gates are there. They provide us with some sort of phase shift. Okay. So without altering the probability of measuring a particular state. Okay. They only introduce phase shift. There is no change in the we can say amplitude of the quantum state. Okay. So or probability of the quantum state. So these gates are crucial for quantum algorithms, quantum interference, and phase-based quantum computing. Okay. So for example, the major gate is S gate. Okay, it provides us with pi by 2 phase shift. When we apply it, but it provides this only to qubit cat state 1. Okay, it does not provide this pi by 2 phase shift to when it is applied to 0 state. 0 state remains as it is. It does not provide any kind of phase shift to 0 state. Similarly, we are having other gates like pi by 4 gate. It is also called T gate. Okay, so it provides us with 45 degree of phase shift. Then general phase shift gate are phi is there. Okay, its matrix representation is like this. If we expand this, it will come into cos into sine kind of things. Okay, so now when this particular kind of general phase shift gate or phi is applied on cut 0, it won't change anything of 0, like it won't change the phase of 0 state. But when we apply this on phase cat state 1, quantum state 1, okay, it gives it a phase shift of whatever phi we would be choosing. Okay, value of phi we would be choosing. For example, these are the specialized cases of general phase shifter gate or phi. Okay, if our phi in that case is pi, then it provides us with poly Z gate, because poly Z gate provides 180-degree phase shift. Okay, if it is its phi value is 0, then it does not provide any kind of phase shift, and it is equivalent to identity gate, which does not perform any kind of, we can say, change on our qubit. Then there is having S gate. S gate provides pi by, if we choose phi value of pi by 2, then it provides us with the functionality of S gate equivalent to S gate. Then if we choose pi by 4, it provides us with functionality of T gate. Okay. So now coming to another very important single qubit quantum gate, that is called U gate, or it is called sometimes it is called Euler gate also. So U gate is basically referred to as a function of three angles, different types of angles like theta, phi, and lambda. Okay, so these three parameters basically allow the construction of any single qubit gate. From this particular gate, we can construct any kind of single qubit gate. Okay, so it is having three different Euler, and these theta, phi, and lambda, these are called Euler angles. Okay, so the value of theta basically it determines how much rotation it will give to our qubit around the x-axis. Okay, in Bloch sphere. Similarly, phi determines what kind of phase shift it would apply to state 1. Okay, then lambda basically determines what kind, if we I need additional phase shift apply to superposition kind of states are there. Okay, for example, I applied Hadamard gate on some input qubits. Okay, it created a superposition state, and I want to change the phase of those states. Then I can choose some value of lambda as per my requirement. Okay, so these are the special cases of U gate. Okay, so if you choose 0, 0, 0, theta, phi, and gamma, sorry, lambda, you choose different values 0, 0, 0, then it will be giving us with identity gate. If I choose these values pi by 2, 0 and pi, okay, for theta, phi, and lambda, then we will be getting the merge gate from it. Okay, similarly all these kind of gates are there, those I can drive from the U gate. Okay, that is why it is sometimes also called universal gate. Okay, but in quantum computing universal gate means we are having a different kind of we can construct any kind of functionality from it. So it we U gate is only for constructing single qubit gates only. Okay, we can drive other single qubit gates from it, not the multi qubit gates. Okay, so these are different types of applications of all the phase gates. They will be widely used in quantum Fourier transform for quantum phase estimation, then controlled phase gates like CZ and CP. Okay, they are widely used in quantum entanglement and interference. Then they fine tune the relative phase between qubit state and states for interference and constructive and destructive kind of effects. Okay, then they are essentially in phase estimation, Grover's algorithm and Shor's algorithm. They are widely used in error correction. Okay, now coming to multi-qubit gates. So multi-qubit gates basically they operate on two or more qubits simultaneously. Okay, so there are four different types of widely used multi-qubit gates. One is controlled NOT gate, which is called C NOT gate. It is widely used for creating the entanglement. Okay, and entanglement is the most important operation in quantum computing. Okay, then swap gate is there, which swaps the two qubits. Okay, if input qubits are 0 and 1, it will swap 0 to 1 and 1 to 0 at the output. Okay, then Toffoli gate is there. Toffoli gate is nothing, it is controlled, we can say C naught, it is controlled C naught gate. Okay, so in C naught gate we are having only one control input control, and other is the target input. Okay, so in Toffoli gate we are having two control inputs and one target input. Then similar to swap gate is Fredgin gate, it is called controlled swap gate. So this is controlled NOT gate. This is the matrix of controlled NOT gate. Okay. So C NOT gate basically flips the target qubit. Okay. If the control qubit is in state 1. If the control qubit is in state 0, then it does not change the state of the control qubit, target qubit. Okay. So for example, our initial state is 0, 1. Okay. So here in this particular notation 0, 1, the first qubit always acts as the control qubit. The second qubit always acts as the target qubit. Now if I apply C naught gate on this particular state 0, 1, okay, cat 0, 1, then in this case qubit 0 is the control, okay, and qubit 1 is the target. So because it cannot change the state of the target qubit, if the control qubit is in 0 state, the state remains unchanged. Okay, now take the second case when psi is equal to get 1, 1. Okay, so now in this case control qubit is also 1 and the target qubit is second qubit, it is also 1. Okay, now if I apply C naught gate on this, okay, because the control qubit is 1, so it will, what it will do, it will flip the second qubit, which is earlier it was 1, it has flipped it to 0. Okay, so now, if I want to create entanglement with C naught and Hadamard gate, how I would be able to create the entanglement? Okay, so apply first we need to apply Hadamard gate on qubit 0. Okay, so this 0 0, it could be written as like first on first qubit I have applied Hadamard gate. Okay, so it we when we apply Hadamard gate on 0, then it is giving us cat 0 plus cat 1 divided by under root 2. Okay, and then it is answered with 0 cat 0. Okay, cut 0 0 can be also written like this. If I apply Hadamard gate on first qubit, then I am getting this kind of output. Okay, cat 0 0 plus cat 1 0, then y under root 2. Now, if I apply C naught gate on this particular output, this one, okay, in this case, this would be acting as first qubit in both the combination 0 0 and 1 0. It would be acting as the control input, control qubit, and second would be acting as the target qubit. Okay, so in first case 0 0 control qubit was 0, so it won't change this. Okay, in second case the control qubit was 1 and target qubit was 0, but it then because the control qubit is 1, it has changed it to second target qubit to 1 1. Okay, so this has given us an entangled Bell state. Okay, so this is how we can create any kind of Bell state. There are 4 Bell states we can create using different combinations of Hadamard and C naught gate. For example, this was for if both the qubits are 0 0. For creating other kind of Bell state, we will take 0 1 1 0 1 1 combination as the input. Okay, so accordingly it will give us different Bell states. So now second important gate is swap gate. Okay, it exchanges the quantum states of 2 qubits. Okay, so it is basically most basic kind of operation for reordering qubits in quantum circuits and is widely used in algorithms, error correction and optimizing quantum hardware constraints. Okay, when we talk about quantum hardware constraints, uh, if you go check the topology of existing quantum processors, okay, so they contain a lot of qubits. Okay, all qubits are not basically connected to each other. Only some specific qubits they are connected to each other. Now, if I want to those kind of limitations of existing quantum hardware, okay, how I can interconnect one qubit to another, then I can obviously use the swap gate. Okay, then in swap gate, for example, there are four input states. Okay, 0 0 0 1 1 0 1 1. So how it will change our input state to output? 0 0 will remain 0 0, 0 1 will become 1 0, and 1 0 will become 0 1. Okay. Similarly, we are having topology gate. Topology gate is nothing. It is controlled in a control C naught gate. We were having only one control input, control qubit. In this, we are having two control qubit. Okay, these solid dots, they represent control qubits. Okay, and this plus sign is representing the target qubit. Okay, so in this case, for example, we are having two qubits. Okay, qubit 1 and qubit 2. Okay, these are the control qubits, and qubit 3 is the target qubit. Okay, so qubit 3 will be only flipped when both the qubits q1 and q2 are 1 1. Okay, so this is below is the given example. If we want to create, we can say check the function of polygate, then we can easily check from this. Here in these all these combination, for example, here only in this particular case, first two qubits are the control qubits. In this particular case, first two qubits are the 1 1. Then only in here in this it will change the third qubit, target qubit to 1 1. All other combinations will remain same. Similar is the controlled swap gate. Okay, so we are having two, we can say controlled. If this is one, then only it will swap the two qubits. Otherwise, it won't change the cube input. We can say whatever quantum states are there. Now, coming to how we can implement these kind of operations on quantum computers, what kind of quantum computing platforms are there? Okay, so where we can implement quantum gates, circuits, or algorithms. So different kind of IBM is providing with different kind of tools. most famous is Qiskit. Okay, so in Qiskit they are also offering IBM Quantum Composer. Okay, Quantum Composer is basically nothing. It is a graphical kind of tool where they provide us with different kind of gates, and we can create circuits from those gates and visualize those circuits in Quantum Composer. Okay, for example, this is the operation, different types of, if I want to implement different kinds of, just you can check this IBM Composer. It is available at this particular hyperlink. Then this is basically just a representation of IBM Quantum Composer. Okay, here all the gates are there. Okay, you can just pick and drop these gates here. Okay, here simultaneously it will giving us the probability of output. Here we can check the phase and state magnitude also. Okay, sorry, state and phase angle of the my output. Okay, so, for example, in this particular slide, we have put Hadamard gate. Okay, what does Hadamard gate do? All the qubits are initially assumed that they are into cat 0 state. Okay, in quantum computing, all the qubits we assume that they are into 0 state. When we apply Hadamard gate, it puts the qubit into superposition state. Superposition state means 50-50% probability of being it to cat 0 as well as cat 1 state. Same, that is why it is representing that it could be my output could be both into 0 and 1 simultaneously. Similarly, we are having other kind of gate, Bell state, how that we were talking earlier. Okay, so we can create Bell state. We are having two qubits now. Okay, Adam, we are having different kind of, we can say Hadamard gate, C0 gate. Okay, so this is basically how it creates the entanglement. Okay, so these are the other kind of, we can say, combination, any kind of gate combinations we can simulate. Okay, in IBM Quantum Composer. So coming to what kind of applications. Yes, there I am seeing some questions that what is Quantum Composer? It is yes, Quantum Composer is simulation tool provided by IBM. Okay, it is a basically graphical user kind of interface IBM has provided. Okay, if you want to implement simple kind of quantum operations, okay, then this kind of tool is very helpful. It can only give us simulations of 5 qubit circuits only. Okay, for if we want to go beyond 5 qubits, okay, then obviously we have to go for Python kind of implementation, and those kind of things we are having Qiskit. Okay, IBM is providing Qiskit. This IBM Composer is simulation kind of tools. So what kind of applications of quantum circuits, or we can say quantum gates, or any kind of quantum system is there? Okay, so quantum is has the we it is anticipated that they might be having lot of applications in cryptography and cybersecurity. Okay, at present, whole of the world is working on quantum technology due to the fear that it can break the existing encryption, like RSA and ECC algorithms. They are being used for securing our internet, security of the internet. Okay, but they once the successful quantum computer come, they would be easily break. It could be easily break these two algorithms, RSA as well as ECC. Okay, so then optimization problems are there. A lot of optimization problems in different kind of areas. Traveling salesman is the example, one of the example. Then in supply chain man optimization, portfolio optimization in finance, banking sector. Then in quantum simulation, simulating all the possible combinations of drugs, genomes, okay, material science, different combinations of molecules for inventing new kind of materials. Then chemical reaction modeling, because in all these combinations, why these kind of we can say applications quantum computer would be helpful, because these kind of applications, there are a lot of combinations of the input, those have to be computed. Okay, and in supercomputer, even on supercomputer, these kind of combinations, if our combination exceeds we can say 70. Okay, combinations, inputs are 70 and total combinations of inputs would be 2 raised to power 70. If we want to compute these kind of things on existing classical supercomputer or machines, then it would take a lot of time. Okay, so in quantum, we have seen that if we are having successful quantum computer with sufficient number of qubits, at present existing qubits, they are having noisy qubit. Okay, so those noisy qubits, they contain lot of noise with them. Okay, they are not stable kind of qubits. So that is why, moreover, we don't have sufficient number of qubits at present with us to simulate these kind of problems. Okay, but people are already started developing their algorithms, okay, on these noisy devices, simulating these algorithms on noisy devices, and even they are even getting some kind of from we can say enhancements in their results as compared to classicals. But till date, if we see that someone has clearly shown that quantum computers can show some kind of application running in much better than, or solving some problem in much better as compared to classical, then till date it has not been demonstrated, and all of the peoples are working on these kind of problem, solving these kind of what kind of problems we are seeing to using quantum computers. So what kind of challenges are there in building quantum circuits or systems? Decoherence is one of the major reason. Okay, it is nothing. Our qubits devices that we use for computing, they are stable for very short duration of time. Okay, so in that short duration of time, I have to read the output from my qubit. Okay, minor interaction with another particle or electromagnetic field or ambient temperature, it collapses the state of my qubit. Okay, so this is the major hindrance. Okay, so because I cannot run very complex combination, complex circuits on my quantum computer, because my qubits are very stable only for very short duration of times. Okay, so coherence time is very less. It should be very high. Okay. So in quantum computer, there are two main parameters, relaxation parameter T1 and T2, coherence time and decoherence time. T1 is basically for how much duration my the amplitude of my qubit state remains stable, and T2 is for how much duration the phase of my qubit state remains stable. Okay. So these two are the basic parameters in quantum processors. Okay, then error correction is there. Okay, so for correcting the error of one qubit, okay, I need additional 7 to 9 qubits. Okay, so means if I want that one of my qubits should remain error free, okay, then I have to use another additional 7 to 9 qubits to correct the error of the my qubit. Okay, so error free qubit in quantum terminology, it is called logical qubit. Okay, it is called logical qubit. Okay, at present all of my qubits are were noisy qubits. Once I get the this fault tolerant qubit, okay, or logical qubit, then only I would be able to, we can say, perform some kind of meaningful operations in quantum circuits or processors. Okay, so although people are developing quantum error correction codes to reduce the errors in their circuits, still lot of work is need to be done. Okay, in classical existing classical computing, what is we can say threshold of error that we can accommodate, or we already it is there. In existing classical computers, there could be one error in 10 raised to power 12 computations. Okay, whereas in existing quantum devices, quantum processors, we are having one error in 10 raised to power 3 to 4 computations. Means in every about 1000 computations, there is one error. Whereas in case of classical, in every 10 raised to power 12 computations, only one error was there. So you can well imagine how much we need to improve the error in existing quantum devices. So other kind of problems in existing quantum devices are like the scalability. Is another challenge. Means how we can increase the number of qubits in existing quantum processors. Okay, so in most of the technologies we have discussed, superconducting qubits are there, trapped ions there, neutral atoms are there. Okay, so increasing the number of photonics kind of processors are there. Increasing the number of qubits is very difficult. Okay, because there are a lot of associated costs. Okay, and moreover lot of noise is there. Okay, so scaling the number of qubits in my quantum processor is not very easy task. Okay, then noise and temperature sensitivity we have already discussed. So then obviously this, as we have already discussed, quantum supremacy and practical application. Till date, no one has demonstrated that quantum computers they can perform a classic some sort of, they can solve some problem in much better way than the classical computers. Although Google has claimed this in 2019, but that claim was we can say disputed by the IBM. IBM claimed that Google did not give the correct figures, correct kind of computations. Okay, so then these kind of addressing these kind of challenges in existing quantum computers, it we need lot of developments in material science. Okay, so we need developments in material science for creating stable kind of qubits. Okay, then engineering also, computer science also. Okay, although lot of progress is being made, still there are lot of hurdles. Okay, for realizing the full potential of quantum devices. So what kind of quantum circuit development tools are available to you? Okay, so IBM is offering their main platform is called IBM Quantum Experience. Okay, and the key software is Qiskit. Okay, so Composer, IBM Composer is part of this IBM Quantum Experience, and for creating bigger circuit or complex circuits, we need Qiskit. Okay, for Python Pro, Qiskit we can do Python programming, write our Python code and run in it. Okay, so IBM is also offering their actual devices, actual quantum computers of 128 qubit. Okay, if you want to run their your circuits on those kind of actual quantum devices, but problem is you can run your circuit only for 10 minutes per month. Okay, these kind of limitations are there, but still it is better. IBM is offering this kind of facility. No other, we can say, company is offering this kind of facility. Google is having similar kind of environment. Okay, now recently Google has also started offering this. They are having 23 qubit superconducting processor. Okay, they started it offering over cloud. Okay, you can run your circuit in Google Colab easily. Okay, lot of examples are there in Google Colab. You can just search. Okay, and run your circuit on Circ. Okay, then Microsoft is offering Azure quantum kind of platform, and their key software is programming software is programming languages q hash quantum hash. Okay, Rigetti is also using providing main platform is called Forest, and key software is PyQuil. Likewise, all kind of companies are there. Okay, this Xenendo is there from Canadian company. They are offering key software is Penny, which is very widely used in quantum machine learning kind of applications. Now, CDAC in India, CDAC has developed their own simulator. Okay, we can say in collaboration with IIC Bangalore and IIT Roorkee. Okay, and this QSIM simulator, quantum simulator. Okay, it is available on this particular link. Okay, or you can just mail on this particular link and they will create your credential for logging into this, or you can experiment with this QSIM simulator. Similarly, Quniverse is there also there. Okay, so Quniverse, in Quniverse you are having similar kind of things like Qiskit is having. Okay, only thing is very limited number of qubits, up to limited number of qubits we can run simulations in both Quniverse and QSIM, like only up to 20 qubits, and in Quniverse we can run up to 34 qubits. Okay, in IBM Qiskit also we can run only simulators are available only up to 34 qubits. Okay. Now coming to second part of my talk, it is on quantum algorithms. So what are basically quantum algorithms? So quantum algorithm is, we can say, it is step by step procedure or a set of instructions designed to run on a quantum computer. Okay. So different kind of we can leverage advantage of superposition, entanglement, and interference to solve different kind of problems. Okay. So why quantum algorithms matter basically? So using quantum algorithms, we can leverage the potential of quantum computers for in different kind of solving different kind of problems in cryptography, in optimization, in okay. There are a lot of things we will discuss one by one. What kind of algorithms are there? Okay. So, however, what the problem is, we don't have fault tolerant kind of quantum computers, which we are still working towards as of we can say today's date. Okay. We can say December 17, 2025. Current quantum devices run small scale versions of these algorithms. For running a quantum algorithm, for we can say, suppose I am having machine learning kind of problems. Okay. So I need my problem is having a data set is having more than 100 features. So I need 100 qubits for the encoding those features. Okay. If I want to encode angle kind of encoding, I want to use. Okay. So that kind of things are not available. 100 qubits are not easily available to me. Okay. So I need actual kind of quantum computers. Although IBM has claimed they have implemented up to 1133 qubits quantum computers, but they are not available to public. Okay, only 150 up to 156 qubits. They are available only for 10 minutes per month. Okay. So now what kind of, there are different types of quantum algorithms. One is quantum search algorithm, prime number factorization algorithm, then simulation algorithms, optimization, quantum machine learning algorithms, linear algebra algorithms are there, communication algorithms are there. So in quantum search algorithm, we are having Grover's algorithm, okay, which can search a particular item in an structured in an unstructured database in we can say unroot n operations only. We can, for example, we are having in classical, if we are having, I want to search, we can say one particular item from 100 items. Okay, what could be the best possible time in classical? It could be 50. Okay, n by 2. Okay, n is 100 and in classical, the best time could be 50. Okay, but in Grover's algorithm, it says that it can search the same item, okay, in an unstructured database within a root of 100 is 10 in 10 searches only. Okay, so it provides us with quadratic kind of speed up over classical algorithms. So other kind of algorithm is Shor's algorithm. Okay, so fact it is used for factoring very large numbers, and it is seen as a threat to the existing RSA and ECC kind of security protocols. Okay, so as we have already seen that multiplication is a very easy. Classical computers can do it very fast. Okay, but if we ask classical computer to factorize a number, okay, then it is very difficult for classical computers. Okay, for example, factoring 391, it would take a lot of time to factor that. Okay, so here comes the Shor's algorithm. Okay, so Shor's algorithm, it promises that it can factorize a large prime number, okay, in polynomial time. Okay, so but provided we are having lot of qubits available in my quantum processor. Okay, till date that is not available. So at present, in the coming 2 or 3 years, it is not a threat basically. Shor's algorithm is not a threat because we don't have that many qubits at present with us. Okay, so now at present, what people are doing harvest later, we can say harvest later, uh, encrypt, sorry, it is called something called you can down people are downloading encrypted data now at present, okay, from of other countries, okay. What they will do when sufficient large quantum computers comes with sufficient number of qubits, they will crack, or we can say they will crack the encryption of those encrypted data using that by running this Shor's algorithm on that particular quantum computer. Okay, these are why it is Shor's algorithm is important. We have already discussed. Then there are other quantum simulation algorithms like Hamiltonian simulations, variation of quantum Eigen solver, quantum phase estimation. Then these have already been discussed, I think, by the earlier speaker from IIT Delhi, quantum key distribution and teleportation. Then in optimization algorithms, I am having quantum approximate optimization algorithms, then variation of quantum algorithms, okay, quantum gradient descent kind of algorithms for different kind of applications. So we are having for linear algebra quantum algorithm, for matrix kind of manipulations, I am having different kind of algorithms like HHL algorithm, quantum singular value transformation, quantum PCA, quantum SBM kind of things are also there in machine learning. Okay. So now coming to quantum machine learning. Okay. So it is, we can say it is intersection of quantum computing and machine learning. Okay, where we can leverage the advantage offered by quantum computers for speed upping our complex machine learning tasks. Okay, so quantum similar to quantum classical machine learning algorithm. In quantum machine learning, I am having different kind of algorithms. Okay, in supervised, I am having quantum supervised, quantum sport vector machine, quantum neural networks for classification and regression kind of things. Okay, in unsupervised learning, I am having quantum PCA, quantum clustering kind of algorithms. Okay, then in a reinforcement learning, I have a quantum reinforcement learning kind of algorithms. Then hybrid algorithms are also there, VQE, variational quantum eigensolver, quantum approximate optimization algorithms. Okay, then this generative models, quantum GANs are recently added. Okay, so what kind of algorithms people have already developed in quantum domain? You can check on this particular site, Quantum Algorithm Zoo. Okay, I think around more than 400 algorithms people have already developed. Okay, in quantum domain, and people are using those kind of algorithms. So what kind of resources are available in quantum machine learning? So Qiskit from IBM, they are offering this Qiskit machine learning 0.8.2 kind of simulation tool, or we can say source, okay, for machine learning, quantum machine learning. Okay, different kinds of examples are there, quantum neural networks to quantum Bayesian interference in inference, sorry, then quantum encoders, quantum convolutional neural networks, everything is there. You can go and check there. Okay, then PennyLane is another very important quantum machine learning resource. Okay, it is open source Python library designed specifically for quantum algorithm development, quantum chemistry, and quantum machine learning only. Lot of examples are there into PennyLane. So now coming to conclusion of my session, okay. So we see that quantum gates and circuits, they form the foundation of quantum computing. So understanding quantum gates or circuits is very essential for developing quantum algorithms. Okay. So what kind of, we can say, future is there of quantum computing? So with advances in qubit scalability or stability or error correction, okay, quantum circuits and algorithms, they may soon, we can say, start solving the real world problems which are beyond the reach of classical systems. Okay, so here I will stop, and my colleague Tarun, he will be demonstrating how we can implement, we can say, quantum gates into Qiskit and on IBM Composer. He will be demonstrating this. Tarun, Tarun. Just a minute, please.
Now, hello. Now, sir, you can unmute yourself. Tarun, sir, unmute
Okay,
yourself. Okay.
okay, okay. Okay, good evening, everyone. So now we are going to do a quick hands-on session on quantum composer, and we will implement some of the quantum gates. So first, let me share my screen. Is it visible to everyone?
Yes, sir.
Okay. Okay, so to access the IBM Quantum Composer, what you need to do is you need to simply go to the browser and type this IBM Quantum Composer, right? And then when you hit enter, it will take you to the IBM Quantum website where you can see the IBM Quantum Composer. Okay, so this is the IBM Quantum Composer where you can create any quantum circuit. And a quantum circuit is nothing but a combination of various quantum gates. So if you look at the left side of the composer, you can see various quantum gates. This one is the Hadamard gate. This is your NOT gate, then C NOT gate. Gurmohan sir has discussed most of all of these gates. So these are the same gates. And if you look at here, these are the number of qubits. Q naught is the qubit at index 1, index 0, and then this is the second qubit, then third, then fourth qubit. So if I want to create the superposition, let's say, so I simply need a single qubit for that. So for that, I need to remove these other extra qubits. And when we take measurements, we always take it on the classical channel. So this is why I have a classical channel over here by the name C1 and a quantum and a qubit which is Q naught, right? So if I implement a Hadamard gate, I simply have to pick and drop on the wire and then apply the measurement. This one is the measurement gate. So as Gurmohan sir has told you about the Hadamard gate, that it puts the qubit into superposition. Let's say if it is a if we apply the Hadamard gate on cat 0, it will give you the plus state, which is cat 0 plus cat 1 divided by square root of 2. So if you look over here, so when we apply Hadamard gate, it will give you the equal superposition of 0 and 1. So if you check here, the probability of state 0 is 50%, and the probability of state 1 is also almost 50%. So it is uh, so now we will going to implement some other gate. So let's say I'm going to implement this NOT gate. So what NOT gate does, it converts state 0 to state 1 and state 1 to state 0, just like the classical NOT gate, right? So the initial state of the qubit is always 0. So when we apply NOT gate on cat 0 and measure the results, and when we check the probability, so it is saying that we are getting the state 1 with 100% probability,
Not
right?
gate here, not gate here is poly X gate basically.
Yeah. So NOT gate is basically the poly X gate. And then let's say we want to implement the C NOT gate, the gate which is used to create the entanglement. So since we know that this C NOT gate is a 2 qubit gate, So for that, to implement the gate, this particular gate, I need 2 qubits. So I have to increase the number of qubits from 1 to 2. So, and also, if you can look here, this is the C naught gate, but I cannot pick and drop it because I do not have 2 wires, 2 qubit wires over here. So then I have to add one more qubit. I have to add one more classical channel, right? Then I can pick and drop this C naught gate, right? And I'll have to measure both of the uh, qubits. So how this C naught gate works? When we apply this, when we give cat 00 to the C naught, it will not do anything. The output will be same as the input. It only works when the control, this dot represents the control and this plus represents the target, right? When this control bit is qubit is 1, then only the target qubit flips, right? So right now I have made it 1 by placing a not over here, not gate over here. So it becomes, the input becomes 1 0. So for 1 0, C naught will give me the output 1 1 because control is 1. Whenever it sees the control is 1, then it flips the target. So here target is 0. Uh, After applying the C naught, it becomes 1. This is why for input 0, for input 1 0, the output is 1 1 with 100% probability. Then we can also implement this 3 qubit gate, which is Toffoli gate. For that, I need 3 qubits. So I will increase one more qubit, and I will also increase one more this classical channel. And this Toffoli gate, it is a 3 qubit. Actually, it is the extension of C naught gate, right? When we have a single control, it is C naught gate. When we have two controls, it becomes Toffoli gate or double controlled NOT gate. Okay, so now if I give input this, if the input for this Toffoli gate is 0 0 0, right? It will not do anything. It will like it is saying that this we are getting the state 0 0 0 with 100% probability, which is the input to this particular gate. Let's say if I change the controls, right? If at the first qubit I am applying a NOT gate, at the second qubit I am again applying the NOT gate. So both the controls are now 1 1. So Toffoli gate works only when the both the controls are 1 1, then only it flips the target. So here the controls are this Q0 and Q1, both are the controls which are at state 1, and then this Q2, this is the target one. Here the input to this Toffoli gate is 1 1 0. If you look at the output, it should be 1 1 1. So here it is 1 1 1, right? And then let's say if I want to implement this Toffoli gate for input 1 1 1, I'm changing the input to 1 1 1. The output should be 1 1 0, right? Because both the qubits are at both the control qubits are at 1 1. Target is also at 1, so target will be flipped to flipped from 1 to 0, cat 0. So it becomes cat 1 1 0. So if you look at here, this is cat 1 1 0. Since this Qiskit, they follow little endian. So in this, we have to read it like backwards, like from the LSB to MSB. So you do not have to read it 0 1 1. It is 1 1 0. You have to read it from right to left. So similarly, let's create this. Let's implement this swap gate. So what swap gate is a 2 qubit gate, right? So let's use it. This is the swap gate, right? Here I am implementing this of swap gate for the input 1 0. The output should be 0 1, right? The both of the uh, inputs will be exchanged at the output, right? A becomes B, B becomes A. So for 1 0 it should become 0 1, right? So here this 1 0, it is after applying the swap gate, it is 0 1, because we are reading it from left to, sorry, from right to left. So this is nothing but the identity gate. uh, if we apply the identity gate, it will not do anything, right? This is just a identity matrix. And now there are these phase gates, this T gate, S gate, Z gate, and the T dagger, S dagger, P, all of them, they are the phase gates, right? So, and also they are the single qubit gates. So if we implement this T gate for state 0, it will give you the state 0, right? It will only work when the uh, input is 1. For input 1, it will add the phase. Since we can only see the probability or the state over here, right? The phase difference cannot be seen in this particular graph, right? And also let me one, let's say for when it is 0, right? This is the phase disk. If you look at here, it is saying that probability of 1 is 0%, right? So when you apply a NOT gate, the phase will be changed, right? So then it says the probability of 1 is also the probability of 1 is 100%. So similarly, we can apply all those phase gates in this circuit composer, quantum composer, by simply picking up the gates and placing it on the these particular wires. And also, if you want to learn more about these gates, so you simply can right click on these gates, and you can simply click on the view info, right? So when you right click on the particular gate and click on view info, it will tell you about the function of the gate, that what it does, right? And there are some links to the Qiskit repository where you can learn more about these gates and the terms which are coming in the description of these gates, right? Similarly, let's say I want to learn about the this T gate, right? So I will simply right click on it and simply click on view. So it will tell you that it will give you the rotation around z axis by the pi by 4 angle, right? So you can simply know about the function of the gate. And here on the right side, if you look at here, this is the quasm, this is the assembly language program. You can also add gates by simply simply by making changes in the program. Let's say I want to add one more not gate at qubit, this q not qubit, right? The first qubit. So I simply, what I did, I simply copied the this sixth row and pasted it, right? Let's say I want to implement a T gate. I will simply copy it and I will paste it. So if you look at here, one more T gate is now added in the circuit, right? So for also you can, what you can do, you can create your IBM login, and you can sign up to the IBM Quantum to this IBM Quantum platform, and then you will be eligible to run your quantum circuit on the real quantum computers, right? For that you need to you need to create the account, and you need to send the jobs to the particular quantum computers. So they have provided us 3 quantum computers. So you can send the jobs on any of the quantum computers. And also there is this Qiskit code, which is compatible with the Python notebooks, right? So you can simply copy these program and you can paste it on the on the notebook, and you can run them directly from the notebook, right? For that you do not need to use the to run these circuits on you do not need the composer. You can simply run these circuits by using the Python programming on the notebook. Uh, so these are this is a very brief overview about this quantum computer, and how we run basic quantum circuits on the quantum composer. Let's make one more circuit of the Bell state. Let's say I'm creating the Bell state for input 0 0. For that, I'll simply need a Hadamard gate on the first qubit and the C naught gate on the second qubit, and then I'll measure both of my qubits. Since we are using two qubits, so for that I'm going to need two classical wires, right? So I'll have to measure it. So the output of the this Bell state is the maximal entangled state, which is cat 0 0 plus cat 1 1 divided by square root of 2. So if you look at the probability of the output of this particular circuit, so you will see that you are getting two states. The first one is cat 0 0 and the second one is cat 1 1, which is theoretically correct, right? And then the probability is 50%, since they have the amplitude component is 1 by square root of 2. If you take the square of it, it will give you the probability. So 1 by square root of 2 squared is equal to 50%, right? So this is why this is almost 50% for state 1 1, and again almost 50% for the state 0 0. So this is how we can implement the Bell states. So this one is for cat 0 0. You can implement it for like cat 1 1. For example, I'm changing the input from 0 0 to 1 1, right? For that we have the uh, Bell state is like 0 cat 0 1 plus cat 1 0 divided by square root of 2. So which is correct. So now we can also run all those gates and all those circuits by using Python on the Jupyter notebooks. So here I have created a notebook. Let me open it. Yeah, so this is the notebook. This is the brief overview about the quantum gates. That quantum gates are nothing but the operations that we can apply on the qubits. And they are reversible in nature. They are nothing but the unitary matrices. So they have to follow the product of unitary matrix along with its transpose should always be equal to identity matrix. So this is what unitary means. So there are two type of gates: single qubit gate, multi qubit gates. And what gates are coming under the single qubit gates category are these poly gates: poly X, poly Y, poly Z gate. H is the Hadamard gate, S is the phase gate, then this T gate, and some of the rotational gates Rx, Ry, and Rz. And what are the multiple qubit gates? These are C naught gate, which is also known as CX gate, then controlled Z gate, controlled Y gate, swap gate, control swap gate, Toffoli gates. Toffoli gate is nothing but the double control NOT gate, right? Then this MCX is multi-control NOT gate, right? So multi-control NOT gate means you can have uh, n minus one number of controls, and your target can be at the nth position, right? So you can extend it like this. And similarly we have multi-control Z gate, right? So the poly X gate is, this is the The poly gates are these are the three poly matrices: poly X, poly Y, poly Z. Right? They are given by the scientist by the name Poly. Right? The X gate matrix, which is the NOT gate, quantum NOT gate. The matrix is X is equal to 0, 1, 1, 0. Right? This is the matrix. When you apply the NOT gate on the state cat 0, it can be implemented like this. Right? And as you can see, after the matrix multiplication, you will see that the final output is cat 1. So this is how we implement the quantum this NOT gate on the cat 0 state, right? So let's say we want to implement it on the implement it by using the Python. So first we have to import some of the necessary libraries like this NumPy, which is for the which is numerical Python for mathematical operations. From math we have imported this pi and square root, right? We have to install some of the Qiskit libraries also, right? We have to install them like pip install Qiskit, pip install Qiskit AER, right? So then after installing those libraries, we can import these classes from these particular libraries, right? So from Qiskit we are going to import this quantum circuit and transpile, right? By using this circuit we can create the quantum circuit, right? And by using this transpile we can convert our quantum circuit into the a transpiled circuit, which are a simulator or you can say the quantum computer understands, right? Then actually the quantum computer, they do not understand these gates like Hadamard gate, right? Or you can say this uh, like T gate, right? So what they do, they have the quantum computers, they have their basis gates, right? So they understand some set of gates. So first they will convert the circuit which is fed to the quantum computer. They will convert the circuit into the gates which the quantum computers can understand, right? So this process is called transpilation, right? After that these circuits will be run on the computer, and then you will get to see the final result. So from this Qiskit AER, we are going to import this AER simulator. Right now we are importing this simulator because we are going to run these circuits on this particular simulator, right? And then this Qiskit visualization, these are nothing but for the plotting purposes. Just like if we want to plot the histogram, we want to plot the state vector on the block sphere. So these libraries needs to be installed, and these uh, tools will be should be imported from these particular libraries, right? And then this from Qiskit.quantum info import state vector. If you want to print, or if you want to do any operations with the state vector, so for that we need this tool also, this state vector from this particular library. So now what I'm going to do, I'm going to create a circuit which implements only a NOT gate, right? For that, I'm going to create a circuit by the name QC, and by using this tool, quantum circuit, I'm going to create a circuit of width 1, right? A single qubit circuit, right? And then I'm going to implement the apply a NOT gate by just like this QC.X. This is how we can implement a NOT gate, right? And then this 0 means the index of the qubit, right? The zeroth qubit, right? So this is the qubit at index 0, right? And then we are going to draw the circuit. So we can draw the circuit simply by writing this qc.draw, and mpl is nothing but the matplotlib, right? It is used just to visualize the circuits better, right? If you do not use this mpl, this visualization will be a black and white circuit. This NOT gate will be a black and white circuit. And then we can plot the block sphere of that, so that we can see how the state has been changed. So as we all know, the initial state of a qubit is always 0. So when we implement a NOT gate on 0, the output will become 1, cat 1, right? So if you plot it on the block sphere, it will say the initial state was 0, but now the state is pointing towards the this 1, right? Now the state is 1. So the NOT gate has been acted perfectly, right? So now we want to implement this circuit, this NOT gate circuit on the simulator, right? For that, we need to measure the output just like we are doing it in the composer, right? Uh, on the composer, we always use these measurement gates, right? So this is nothing. Here I'm measuring this first qubit. Here I'm measuring the second qubit. So I'm measuring all of the qubits, right? This is why this measurement can be done by using the measure all operation, where it is measuring all the qubits. Then the simulator which I'm going to use is the AER simulator, right? Which I have imported from the Qiskit AER library. And then this QC, the circuit name is QC. It will be transpiled to the according to the basis gates of the simulator, right? This is why I'm going to transpile this particular circuit. Now I'm going to run this circuit on the simulator like this: simulator.run qc.result, and then I'm taking out the result, and I'm going to plot it in the form of histograms, right? When I plot it, I can see the output is 1 with probability 100%. Since we have run this particular circuit for 1024 shots, right? So for all the shots, it has given me the output 1, right, for input 0. So this which is nothing but a basic operation of a NOT gate. So now I'm going to implement two NOT gates, right? Two NOT gates are implemented like this. So it will give me the input state at the output, right? The input is 0, then first NOT gate will flip it from 0 to 1, then second NOT gate will flip it from 1 to 0, right? So which means these gates are reversible in nature. When you apply them twice, they will give you the original state which is at the input, right? Now if you plot it on the block sphere, it is at 0 because we have started from 0. We implemented two NOT gates, then again we reached to 0. So if you run it on the simulator like this, right, it will say you are getting 0 with 100% probability. And then we have these Y gates and Z gates, right? Y gate is nothing but the combination of Z gate and NOT gate, and Z gate is nothing but it adds a negative phase of -1, or you can say phase of pi on the state 1, right? For state 0, it will not do anything; it will keep it unchanged, right? When you implement this Y gate, it is like this, right? And when you plot the block sphere, you will see the output for the input 0. You will get the output for input 0. You're getting is 1, right? In this block sphere, you cannot see the phase changes, right? You can only see the state changes, right? For Z gate, this is how you can implement Z gate qc.z, right? Now we are going to draw it qc.draw mpl, and then we are going to plot it on the block sphere, right? So for state 0, it will give you the output 0. So this is why it is at 0. For state 1, it will give you -1, but you cannot see the phase changes on the block sphere. Then we have this Hadamard gate, which puts the qubit into superposition of 0 and 1. So this is the matrix of Hadamard gate. When you apply Hadamard gate on 0, it will give you a plus state. When you apply it on the 1 state, it will give you the minus state. The plus state is this, and the minus state is this second one, right? Now this is how you can implement the Hadamard gate by simply writing this qc dot h at qubit which is at index 0, right? And then you can plot the plot it on the block sphere. So this is the output will be on the x-axis because it has 50% component of this 0 and 50% component of this 1. And when you run it on the simulator, it will give you the actual result, which is 509. Like we have run it for the 1024 shots. So 50% it has given us state 0, 50% it has given us state 1. Like it is a linear combination of both 0 and 1 with equal probabilities. And then we have created one more circuit by the and we have used this combination Hadamard gate, Z gate, and then Hadamard gate. These three gates have been implemented. So this is nothing but like by using these three gates we can implement a NOT gate, right? So this NOT gate is also equivalent to this combination Hadamard gate, Z gate, and then again Hadamard gate. So we have implemented these gates for state 0. The output should be state 1 because they are simply giving us the output of Hadamard gate, sorry, the NOT gate. And then C NOT gate. C NOT gate is nothing but the gate which acts only when the control is 1, right? Here we have made the control 1 by setting this qubit to 1 by using this NOT gate, right? Now the input is 1 0, the output should be 1 1, right? So when you plot the block sphere, it will say the output is 1 and then 1 1 1. We can only like visualize a single qubit rotation on the block sphere. So for this is a 2 qubit. For that we are going to use 2 block sphere. This is why it is saying that one this is qubit at state 1, and this the second qubit which is at state 1, right? For input 1 0, the output is 1 1. After running it on the simulator, it is saying we have got this 1 1 with 100% probability. Since we have run for the 1024 shots, for all the shots it has given us 1 1. And then this Toffoli gate, which is nothing but a double control NOT gate, the extension of C NOT gate, right? So when we want to implement the Toffoli gate on the notebook, we can implement it like this: qc.mcx 01 as a list, and then this 2. Since this is a 3 qubit gate, we are going to use the 3 qubits. This is why this circuit has the width of 3, right? Like 3 qubits are there, and then at qubits which are at index 0 and 1, they are acting as the control, and the qubit at index 2 is the target, right? Qubit at index 0 and 1, they are the control. This is why dot sign is there. And qubit at target is this qubit q2 is the target, right? And mcx means multi-control NOT gate. So it is not like you can only implement the Toffoli gate like this. You can implement uh, any multi-control NOT gate, like of any size, right? Where the controls can be n minus 1, and the target should can be will be the nth qubit, right? So when we plot the block sphere representation of this implementation, so this one is for 0 0 0 input. For 0 0 0, the output is always 0 0 0. This is why it is at 0 0 0, right? And if we implement it for 1 1 0, we have made it the qubit 0 and qubit 1 1 1 by placing a simply placing a NOT gate in at the beginning. And so here the input is 1 1 0. For state 1 1 0 as an input, the output should be 1 1 1, right? Because both the controls are 1. When both the controls are 1, the target flips, right? So the output should be 1 1 1. So this is why it is 1 1 1. And when we implement it on the simulator, it will show you are getting the state 1 1 1 with the 100% probability. So now similarly we can implement the control Z gate, right? For state 1, the control for when the input is 1 1, the output will be minus 1 1 for control Z gate, right? So for input 1 1, we are getting this 1 1, but you are not able to see the negative phase because the state vector, this block sphere can only represent the states, not the phases. Now this multi-control Z gate. So by using this MCP means, as we have already covered, that the Z gate is nothing but but a phase gate with pi rotation around the Z axis, right? So MCP means multi-controlled phase gate. So with pi, NP dot pi means you are it is taking a pi rotation, where 0 1 are the controls, and this is the target. So these two, the q at q0 and q1, they are the controls, and this q2 is the target. So when you implement it for the state 111, it will give you the output as minus 111, since we cannot see it on the simulator. Like phases cannot be read from the block sphere, right? This is why you can only see the state 111. But if I want to print the actual state from the particular state vector, you can plot it like this: state is equal to state vector from state vector is nothing but the it is a class which is derived, which we have imported from the qskit.info, right? Here at the very beginning, we have imported it from here, qskit.quantuminfo import state vector. So it has all the information about the states, and also about the phases. So if we want to implement it, you can implement it like this, and then it is saying that it has a negative phase. Negative, the actual state is minus 111. When we run it on the simulator, you are getting to know that the output is 111 with 100% probability. Now this swap gate, it can be implemented like this: qc.swap. We are implementing the swap gate on the input 10, because we have made the q0 state 1, right, by implementing a NOT gate. So input is 10, output should be 01. The outputs will be swapped, right? The output for this q naught becomes 0, and output for q1 becomes 1. So it is 0. For this it becomes 1. So input at the output, both the inputs are swapped. If you run it on the simulator, right, when you look at the result, the output is 0 1, because it follows little Indian. You have to read it backwards from right to left. So output is 0 1 with 100% probability. Similar to this, we have this control swap, where we have a control. When the control is qubit at the control is 1, then only the targets will be swapped, right? For this we have input 1 1 0. Since the control is 1, so swapping will take place. So the output should be 1 0 1, right? 1 1, and then this will be at the output 0, and then this will be at the output 1. So output should be 1 0 and then 1. So if you want to print the state, it is 101. When you run it on the simulator, it will tell you you have got this 101 with 100% probability. Then we have this phase gate. This is the matrix of phase gate. When this phi is equal to pi, the phase gate will act as Z gate. When this phi becomes pi by 2, this phase gate will be acting as T gate. When this phi becomes S gate, the phase gate will become pi by sorry. When this phi becomes pi by 2, this phase gate will act as an S gate, right? So this is how you can implement a phase gate, by simply writing this qc.p. P means phase, and pi by 4 means the rotation that this gate is going to take, right? And this 0 means that this gate is acting on the qubit which is at index 0, right? So this is the circuit. I have implemented a NOT and then a phase gate. So it is showing me the output is 1, because all the changes has been made in the phase. For state 0, it will not do anything. The state 0 will be remained as state 0. The state 1 will be changed, because its phase will be changed. So if you want, when you print the state, it says that this is the state 1 with this one is the phase, square root of 2 plus square root of 2i divided by 2. this is the phase that has been added because of the T gate. This T gate. I'm calling it T gate because when you keep the angle pi by 4 for the phase gate, it behaves as a T gate. And then this rotational gates, this is similar to the phase gate. This gate will rotate the state vector around the z-axis, right? And the rotation will be done by this angle pi by 4, right? So this is how the block sphere looks for this particular state. And when you print the state, uh, this is the phase that has been added because of the rotational gate. And when let's say we want to implement the bell state that we have already done in the composer, right? So we can simply construct it by using the Hadamard gate and then the C naught gate. We have implemented a Hadamard gate, then a C naught gate, and then we have applied we have run the circuit on the simulator, right? And then at the output, the output has to be cat 00 plus cat 11 divided by root 2. It means root 2 square of the 1 by root 2 is the probability of each state, right? So it means you will get cat 00 with 50% probability and cat 11 with 50% probability. So you are getting this cat 00 with 50% probability and cat 11 with 50% probability, right? Okay, so this is all about the quantum gates. So what we have done, we have covered most of the gates, single qubit gates and multi-qubit gates, and we have run them on the simulator as well as, sorry, we have run them on the composer as well as on the notebook. So if you have any questions, you can ask now.
Okay, participants, if you have any question, you can ask. I think there are some questions in chat box.
Okay. Let me.
Okay, what type of a circuit can be implemented using quantum gates? And which simulation tools? Okay, so you have already
Okay.
explained all the. Yes.
Any circuits that can be made out of these gates, these quantum gates, can be can be implemented on the composer, right? Even you can implement the classical gates by using the quantum gates,
Hmm.
right? That can also be done.
Yes, sir.
And even most of the quantum algorithms, they are nothing but the quantum circuits, and quantum circuits are nothing but the combination of multiple quantum gates. So if you think to implement some basic or some low width quantum gates, low width quantum algorithms that can be implemented on the quantum composer and by using the quantum gates.
Okay, next question is
So
related to.
elaborate on quantum composer
You
too.
have
I
already
think I have
explained.
already
Yes,
done
yes,
it.
yes, yes.
Is it
And
quantum bits represented in the Galois field form? No, no, they are different. They are not the
Glasses,
same.
glasses field is different. That is for classical only. For
Yeah,
quantum, we use direct notation or vector notation for representing the
yeah,
qubits.
yeah.
okay,
Maybe
so
some operations are same, some matrix multiplications are there, but they are different in nature. They are classical and not quantum in nature.
okay, okay.
Please
Thank
share
you.
this notebook for
Uh,
Yeah, yeah. I'm going. I will share the notebook. Okay, so that is all from my side.
sir. Okay, sir. Thank you so much, Tarun sir and Gurmohan sir, for this interesting and very knowledgeable and enriching lecture on quantum gates and algorithms. And once again, thank you, sir, for your kind support and participation in Atal FDP on emerging frontiers in quantum technology and communication. Uh, Participants, please mark your attendance on Google Sheet for both the sessions. And tomorrow at 6 p.m., we will meet once again for the upcoming session.
Okay, thank you. Thank you,
Thank you so much,
everyone.
sir.
Okay, sir.
Thank
Thank
you
you.
so much, sir. Dr. Himanshu, please stop the recording.
Thank you, sir.